In mathematics, a dynamical system is a concept in mathematics where a function describes the time dependence of a point in a geometrical space. Examples include the mathematical models that describe the swinging of a clock pendulum, the flow of water in a pipe, and the number of fish each springtime in a lake. At any given time, a dynamical system has a state given by a set of real numbers that can be represented by a point in an appropriate state space. The evolution rule of the dynamical system is a function that describes what future states follow from the current state. Often the function is deterministic. In other words, for a given time interval only one future state follows from the current state. However, some systems are stochastic, in that random events also affect the evolution of the state variables. Overview. The concept of a dynamical system has its origins in Newtonian mechanics. There, as in other natural sciences and engineering disciplines, the evolution rule of dynamical systems is an implicit relation that gives the state of the system for only a short time into the future. To determine the state for all future times requires iterating the relation many times, each advancing time a small step. The iteration procedure is referred to as solving the system or integrating the system. If the system can be solved, given an initial point, it is possible to determine all its future positions, a collection of points known as a trajectory or orbit. Before the advent of computers, finding an orbit required sophisticated mathematical techniques and could be accomplished only for a small class of dynamical systems. Numerical methods implemented on electronic computing machines have simplified the task of determining the orbits of a dynamical system. For simple dynamical systems, knowing the trajectory is often sufficient. But most dynamical systems are too complicated to be understood in terms of individual trajectories. The difficulties arise because the systems studied may only be known approximately, the parameters of the system may not be known precisely, or terms may be missing from the equations. The approximations used bring into question the validity or relevance of numerical solutions. To address these questions, several notions of stability have been introduced in the study of dynamical systems, such as Lyapunov stability or structural stability. The stability of the dynamical system implies that there is a class of models or initial conditions for which the trajectories would be equivalent. The operation for comparing orbits to establish their equivalence changes with the different notions of stability. The type of trajectory may be more important than one particular trajectory. Some trajectories may be periodic, whereas others may wander through many different states of the system. Applications often require enumerating these classes or maintaining the system within one class. Classifying all possible trajectories has led to the qualitative study of dynamical systems, that is, properties that do not change under coordinate changes. Linear dynamical systems and systems that have two numbers describing a state are examples of dynamical systems where the possible classes of orbits are understood. The behavior of trajectories as a function of a parameter may be what is needed for an application. As a parameter is varied, the dynamical systems may have bifurcation points where the qualitative behavior of the dynamical system changes. For example, it may go from having only periodic motions to apparently erratic behavior, as in the transition to turbulence of a fluid. The trajectories of the system may appear erratic, as if random. In these cases it may be necessary to compute averages using one very long trajectory or many different trajectories. The averages are well defined for ergodic systems, and a more detailed understanding has been worked out for hyperbolic systems. Understanding the probabilistic aspects of dynamical systems has helped establish the foundations of statistical mechanics and of chaos. History. Many people regard Henri Poincaré as the founder of dynamical systems. Poincaré published two now classical monographs, New Methods of Celestial Mechanics, and Lectures on Celestial Mechanics. In them, He successfully applied the results of their research to the problem of the motion of three bodies and studied in detail the behavior of solutions. These papers included the Poincare recurrence theorem, which states that certain systems will, after a sufficiently long but finite time, return to a state very close to the initial state. Alexander Lyapunov developed many important approximation methods. His methods, which he developed in 1899, make it possible to define the stability of sets of ordinary differential equations. He created the modern theory of the stability of a dynamic system. In 1913, George David Birkhoff proved Poincaré's last geometric theorem, a special case of the three-body problem, a result that made him world-famous. In 1927, he published his Dynamical Systems. Birkhoff's most durable result has been his 1931 discovery of what is now called the ergodic theorem. Combining insights from physics on the ergodic hypothesis with measure theory, this theorem solved, at least in principle, a fundamental problem of statistical mechanics. The ergodic theorem has also had repercussions for dynamics. Stephen Smale made significant advances as well. His first contribution is the Smale horseshoe that jump-started significant research in dynamical systems. He also outlined a research program carried out by many others. Alexander Mikhailovich Sharkovsky developed Sharkovsky's theorem on the periods of discrete dynamical systems in 1964. One of the implications of the theorem is that if a discrete dynamical system on the real line has a periodic point of period 3, then it must have periodic points of every other period. Basic definitions. Our dynamical system is a manifold M called the phase space endowed with a family of smooth evolution functions phi t that for any element of tt, the time, map a point of the phase space back into the phase space. The notion of smoothness changes with applications and the type of manifold. There are several choices for the set T. When T is taken to be the rails, the dynamical system is called the flow, and if T is restricted to the non-negative rails, then the dynamical system is a semi-flow. When T is taken to be the integers, it is a cascade or a map, and the restriction to the non-negative integers is a semi-cascade. Examples: the evolution function phi t is often the solution of a differential equation of motion. The equation gives the time derivative, represented by the dot, of a trajectory x on the phase space starting at some point x0. The vector field v is a smooth function that at every point of the phase space M provides the velocity vector of the dynamical system at that point. Given a smooth phi t, an autonomous vector field can be derived from it. There is no need for higher-order derivatives in the equation, nor for time dependence in v because these can be eliminated by considering systems of higher dimensions. Other types of differential equations can be used to define the evolution rule. Is an example of an equation that arises from the modeling of mechanical systems with complicated constraints. The differential equations determining the evolution function phi t are often ordinary differential equations. In this case, the phase space M is a finite-dimensional manifold. Many of the concepts in dynamical systems can be extended to infinite-dimensional manifolds, those that are locally Banach spaces, in which case the differential equations are partial differential equations. In the late 20th century, the dynamical system perspective to partial differential equations started gaining popularity. Further examples: logistic map, complex quadratic polynomial, dyadic transformation, tent map, double pendulum, Arnold's cat map, horseshoe map. Baker's map is an example of a chaotic piecewise linear map. Billiards and outer billiards. Acute NON map, Lorentz system, circle map, Rossler map, Kaplan-York map, list of chaotic maps, swinging Atwood's machine, quadratic map simulation system, bouncing ball dynamics, linear dynamical systems. Linear dynamical systems can be solved in terms of simple functions and the behavior of all orbits classified. In a linear system, the phase space is the n-dimensional Euclidean space, so any point in phase space can be represented by a vector with n numbers. The analysis of linear systems is possible because they satisfy a superposition principle. If U and W satisfy the differential equation for the vector field, then so will U plus W. Flows for a flow. The vector field phi is an affine function of the position in the phase space, that is, with A matrix, B a vector of numbers and X the position vector. The solution to this system can be found by using the superposition principle. The case B0 with A equals 0 is just a straight line in the direction of B. When B is 0 and A 0, the origin is an equilibrium point of the flow, that is, if x0 equals 0, then the orbit remains there. For other initial conditions, the equation of motion is given by the exponential of a matrix. For an initial point x0, when B equals 0, the eigenvalues of A determine the structure of the phase space. From the eigenvalues and the eigenvectors of A, it is possible to determine if an initial point will converge or diverge to the equilibrium point at the origin. The distance between two different initial conditions in the case A0 will change exponentially in most cases, either converging exponentially fast towards a point, or diverging exponentially fast. Linear systems display sensitive dependence on initial conditions in the case of divergence. For nonlinear systems, this is one of the conditions for chaotic behavior. Maps a discrete time. Affine dynamical system has the form of a matrix difference equation, with a matrix and B a vector. As in the continuous case, the change of coordinates xx plus 1b removes the term b from the equation. In the new coordinate system, the origin is a fixed point of the map and the solutions are of the linear system ANX0. The solutions for the map are no longer curves, but points that hop in the phase space. The orbits are organized in curves, or fibers, which are collections of points that map into themselves under the action of the map. As in the continuous case, the eigenvalues and eigenvectors of A determine the structure of phase space. For example, if U1 is an eigenvector of A, with a real eigenvalue smaller than 1, then the straight lines given by the points along alpha U1, with alpha r, is an invariant curve of the map. Points in this straight line run into the fixed point. There are also many other discrete dynamical systems. Local dynamics. The qualitative properties of dynamical systems do not change under a smooth change of coordinates. A singular point of the vector field equals 0 will remain a singular point under smooth transformations. A periodic orbit is a loop in phase space, and smooth deformations of the phase space cannot alter it being a loop. It is in the neighborhood of singular points in periodic orbits that the structure of a phase space of a dynamical system can be well understood. In the qualitative study of dynamical systems, the approach is to show that there is a change of coordinates that makes the dynamical system as simple as possible. Rectification. A flow in most small patches of the phase space can be made very simple. If y is a point where the vector field v0, then there is a change of coordinates for a region around y where the vector field becomes a series of parallel vectors of the same magnitude. This is known as the rectification theorem. The rectification theorem says that away from singular points the dynamics of a point in a small patch is a straight line. The patch can sometimes be enlarged by stitching several patches together, and when this works out in the whole phase space M, the dynamical system is integrable. In most cases, the patch cannot be extended to the entire phase space. There may be singular points in the vector field equals 0, or the patches may become smaller and smaller as some point is approached. The more subtle reason is a global constraint, where the trajectory starts out in a patch, and after visiting a series of other patches comes back to the original one. If the next time the orbit loops around phase space in a different way, then it is impossible to rectify the vector field in the whole series of patches. Near periodic orbits in general, in the neighborhood of a periodic orbit, the rectification theorem cannot be used. Poincaré developed an approach that transforms the analysis near a periodic orbit to the analysis of a map. Pick a point x0 in the orbit gamma and consider the points in phase space in that neighborhood that are perpendicular to V. These points are a Poincaré section S of the orbit. The flow now defines a map, the Poincaré map F, SS, for points starting in S and returning to S. Not all these points will take the same amount of time to come back, but the times will be close to the time it takes x0. The intersection of the periodic orbit with the Poincaré section is a fixed point of the Poincaré map F. By a translation, the point can be assumed to be at x equals 0. The Taylor series of the map is f equals jx plus o, so a change of coordinates h can only be expected to simplify f to its linear part. This is known as the conjugation equation. Finding conditions for this equation to hold has been one of the major tasks of research in dynamical systems. Poincaré first approached it assuming all functions to be analytic and in the process discovered the non-resonant condition. If λ1, λ are the eigenvalues of J, they will be resonant if one eigenvalue is an integer linear combination of two or more of the others. As terms of the form λI occurs in the denominator of the terms for the function h. The non-resonant condition is also known as the small divisor problem. Conjugation results. The results on the existence of a solution to the conjugation equation depend on the eigenvalues of J and the degree of smoothness required from H. As J does not need to have any special symmetries, its eigenvalues will typically be complex numbers. When the eigenvalues of J are not in the unit circle, the dynamics near the fixed point x0 of f is called hyperbolic, and when the eigenvalues are on the unit circle and complex, the dynamics is called elliptic. In the hyperbolic case, the Hartmann-Grobman theorem gives the conditions for the existence of a continuous function that maps the neighborhood of the fixed point of the map to the linear map Jx. The hyperbolic case is also structurally stable. Small changes in the vector field will only produce small changes in the Poincaré map, and these small changes will reflect in small changes in the position of the eigenvalues of J in the complex plane, implying that the map is still hyperbolic. The Kolmogorov-Arnold-Moser theorem gives the behavior near an elliptic point. Bifurcation theory. When the evolution map phi t depends on a parameter mu, the structure of the phase space will also depend on this parameter. Small changes may produce no qualitative changes in the phase space until her special value mu0 is reached. At this point the phase space changes qualitatively and the dynamical system is said to have gone through a bifurcation. Bifurcation theory considers a structure in phase space and studies its behavior as a function of the parameter mu. At the bifurcation point the structure may change its stability, split into new structures, or merge with other structures. By using Taylor series approximations of the maps and an understanding of the differences that may be eliminated by a change of coordinates, it is possible to catalogue the bifurcations of dynamical systems. The bifurcations of a hyperbolic fixed point x0 of a system family f mu can be characterized by the eigenvalues of the first derivative of the system, df mu, computed at the bifurcation point. For a map, the bifurcation will occur when there are eigenvalues of df mu on the unit circle. For a flow, it will occur when there are eigenvalues on the imaginary axis. For more information, see the main article on bifurcation theory. Some bifurcations can lead to very complicated structures in phase space. For example, the Ruel-Takens scenario describes how a periodic orbit bifurcates into a torus and the torus into a strange attractor. In another example, Feigenbaum period doubling describes how a stable periodic orbit goes through a series of period doubling bifurcations.